Hi, welcome to another lecture on Calculus 3. Today we are going to do a problem related to topics we see in chapter 12. We want to calculate velocity, acceleration, unit tangential vector, unit normal vector, curvature. These are the topics that we see in this section. Uh, our particle is moving according to this formula, so we have a cosine of omega t in direction of I plus b sine of omega t direction j. I'm going to use capital A for acceleration so it doesn't get confused with this dimension a over there. And you remember that we have these basic formulas here for velocity, acceleration, tangential vector, normal vector. And this is covered in one of the lectures. And we have several formulas for the curvature. You can use any of them. I'm going to probably use the very first one. Okay, the problem we are going to look at is just straightforward. It just requires quite a bit of writing, and everything has to be written carefully so that we don't get confused on the details of this problem. So I'm going to do a little bit of acceleration abbreviation so that my writing becomes a little bit shorter than would be otherwise. So I'm going to have C represents that first function cosine of omega t, and I let S to be the second function sine of omega t. Okay, so instead of 7 characters I'm just writing 1. That's going to be a little bit to our advantage. Let's notice the derivative of these things. I have to take all these derivatives. So I'm going to need what is the derivative of C. So C prime, what's that going to be? Taking the derivative of that omega comes out, sine becomes cosine becomes sine. And similarly, if I take a derivative of S, that's going to be omega times cosine of omega t. So you notice C prime is just minus omega s, and S prime is just omega c as a matter of our abbreviation. So my function now is R is A cosine of omega t, just write C, I, and B sine of omega t, which we just write S, and then J. Okay, so and that way we keep track of everything without writing too much. Now, first item, what is velocity? Well, that's going to be easy. Velocity, I just have to take a derivative of this. So velocity is R prime, so that's going to be A C prime I plus B S prime J. So that's going to be C prime, remember omega minus omega S, minus A omega S I, and then S prime is omega C, so it's going to be B omega C J. By the way, if you feel more comfortable just writing the entire function, be my guest, just go ahead and write the whole thing. Use a big piece of paper and write clean and white, and everything will be fine. So that is our velocity. How about acceleration? So acceleration is, of course, R double prime, or if you wish, it's V prime. So I have to take a derivative of this thing again. So it's going to be minus A omega S prime I plus B omega C prime J. And you remember S prime is just omega C, so I'll have minus A. I have an omega, another omega squared, Ci, and then C prime is minus omega S, so that's going to be minus B omega squared Sj. If you want to clean it up a bit, acceleration, I can factor minus omega squared out of that. I have Ac I plus Bsj. Of course, you notice something you could see from outset. This is R again. So this r here, same as the expression in here. So if you want to write it even shorter, minus omega squared r. Okay, that was the end of easy stuff. Next, we see that we have an expression like v dot v or v squared, and so we might as well go ahead and have those items ready. So I'll let me perhaps put my results in some boxes. So I'm gonna choose a box and choose my box to be red. Let's see if I can do that. Maybe not. So that's my V, and this is my A. Now we are going to go ahead and try to calculate speed. Speed, of course, is absolute value of velocity, or if you wish, it's square root of v dot v. So I go ahead and calculate what, so v dot v, or in other words, just absolute value of v squared. Take this thing dot with itself, so I'm going to have a squared omega squared s squared plus b squared omega squared c squared. I dot I is 1, j dot j is 1, I dot j is 0, and so on. So if you wish to clean up again, omega squared can be separated, b squared c squared. Just remember again, s represents sine of omega t, c represents cosine of omega t, so that's an abbreviation for that. So if I want the speed itself, so here was my velocity, here's my acceleration, here's my speed. I've taken square root of omega. In these problems, omega is always assumed positive, so we don't have an issue with the square root of that. So this is going to be omega, and then a squared s squared plus b squared c squared. So that's our speed. Let's go ahead, put these things in some boxes too, because later on we are going to come and just use these things. Well, what else? Let's collect all of our ingredients and then put them to use. I got my v dot v or v squared, and I have my absolute value of v. I have those. I need a dot v, so let me go ahead and do that. So what is a dot v? Very easy. You have a here, you have v here, so just dot the two of them. So I have minus omega squared ACI plus BSJ, and I'm dotting this thing with the other one, which is minus A omega SI plus B omega CJ. Maybe it would have been nice to factor a omega out of this one as well. Let me go ahead and do that. Just factor the omega here and put it on top of that. So minus omega cubed ACI plus BSJ dotted with minus ASI plus BCJ. So we have to be very careful with our C's and S's. The whole problem revolves around keeping track of all these little things. So minus omega cubed. So I and dotted with I is 1, I dotted with j is 0, and so on. So I will have this is minus a squared cs and the other one is plus b squared c or sc or cs, however you want to look at it. So I get so let's factor cs also outside, so I'll have omega cubed, and then I have a c and s, and let that minus come into my parentheses, so I'll have a squared minus b squared. So let's summarize this. What we got, a dot v is frequency cubed cosine of omega t sine of omega t times a squared minus b squared, and let's put that in a box as well. I meant it to be red, of course. Let's see, it didn't pick. Well, we are going to do more of these things, and gradually these things are going to get a bit more and more complicated. You might be wondering, what is this thing anyway? What does that mean? So what is this kind of a motion? Well, this is the x component of it. This is the y component of it. So if I take x and divide by a, I just get cosine. Y divided by b, I get sine. And of course we know sine squared plus cosine squared is 1. So this motion, if you want to represent what it is x over a. X over a is cosine squared, and then y divided by b is just sine squared, and sum of square of those, of course, is 1. So you know from college algebra, this is just an ellipse. So if a is larger than b, it's going to look like this. If b is larger than a, it's just going to be vertical. So this is a, this is b. So this is a motion that is going on an ellipse. And well, we need to give more details about what kind of motion it is and such. And the detail of this problem is going to reveal the properties of this movement. So there's some particle that's going around on this ellipse, and we are finding variety of things for it: velocity, acceleration, tangent vector, normal vector, and so on. So what's let's remember, what was the tangent vector? Tangent vector, well, it's tangent to your trajectory. It's of length 1. How about normal vector? So normal vector is perpendicular to the tangent vector. It's also of length 1. It's gets to be used for normal component of acceleration and so on. So these are the issues that you see in dynamics. Actually, in your dynamics classes, you're going to find out these quantities for variety of movements in 2 dimensions or 3 dimensions. Okay, so what is next? We pretty much have all the ingredients. I have calculated a dot n, which is used here, v dot v. Let's see, did we use a dot v? Yes. So now I need my n before I calculate a dot n. So before we go any further, let's get t first. That's going to be easy. N, well, n is a bit messier. It's going to take a little bit longer time to figure out what n is. And once we get the n, calculating a dot n or curvature is going to be easy. So let's go after t. So what does t? Unit tangent vectors. We just take the velocity, divide by the length of velocity, and we're done. So here's my velocity. Okay, so here's my velocity. Here is the length of that velocity. So if I take this, divide by that, I get my t. That's as simple as that. So if I want to calculate t, you said that's v divided by length of v. So I have my v here. So I'm just going to copy this through should have factored that omega there, but that's okay. Minus a omega SI plus b omega Cj. That's the velocity, and the absolute value of this velocity is omega times that square root, so a squared s squared plus b squared c squared. So this omega and this omega cancel, and I have minus a s I plus b c j divided by the length of this, which is a squared s squared plus b squared c squared. Again, remember what this thing is. Like if you're working a problem from homework and such, this is really what you have to enter there is sine of omega t plus b cosine times I, b cosine of omega t times j over then radical a squared sine square of omega t plus b squared cosine square of omega t. After you write these lengthy expressions, you appreciate that abbreviation. If you keep track of it, it helps us avoiding a variety of mistakes. Okay, so that is our t. So one more red box here. So let me write t is equal to, here's an expression and here's a expanded expression. Next up, so I got my t. This is the expression for this tangent vector. Now I want to go after n. Okay, n is a ratio of two things. Each of them are kind of substantial, so we better break it up into parts so we don't write too much and we don't get ourselves confused. So I go after this numerator first. Calculate that, and denominator is just absolute value of numerator. So I'm gonna give it a name so we keep track of what that thing is. So I'm gonna say what w is. I'm gonna define w to be numerator of that expression, just so that I break the things into pieces to avoid mistakes that occur when we just deal with lengthy expressions. So, well, good that I have all the ingredients. All I have to do is just write it out. So, first we have a itself. A is the acceleration. You remember, so acceleration, let me write acceleration minus a here. I'm going to copy here this acceleration. Let me write it this way. This is this acceleration, or if you want to factor it, either way. So minus a omega squared ci a omega squared ci minus b omega squared sj. V dot v, what was v dot v? Is this expression. So I'm going to write that. Omega squared, let me just multiply it through. I take omega squared, multiply it through with this thing. So we have omega squared a squared s squared plus omega squared b squared c squared. That is, so far this is my a and this is my square of velocity minus, now I have to write this one, v was, well, what was v? So that's why you need a big piece of paper and be able to look at everything. So rv, this is my v, so I'm going to copy that through. So I have minus, and then that was minus a w s a omega si plus b omega c j. Is that right? That was my velocity a minus a omega si b omega cj. That's what I wrote here. And then a dot v, and let's see if we can go fish a dot v. Here's my a dot v is omega cubed cosine sine a squared minus b squared. Okay, this is the numerator of that expression, and it's supposed to be divided by its length in a denominator. So imagine trying to write all of that. It's not going to be practical, so we broke it up into pieces to be able to handle. So this is the velocity, and this is what a dot v was. Now we have to actually multiply. So all we are doing is very basic algebra, like algebra that you did in algebra 1 really, but there's just so much of it, and then you have to keep on top of the whole thing and not lose track of anybody in this situation. So I have a vector times a number, another vector times some other number. This vector has components I and j, another I and j here. So let me collect all of my i's in one place, all of my j's in one place, and clean it up, see what happens. So I'm going to write I, and then I'm going to write everything that is a multiple of I, collect all of them in one place. I see lots of stuff, so I'm making a lot of room. And then I'll have another thing for j vector, and then I'm going to collect all of those things for the j vector. So I have to take this. I have to take this. Remember, this is a number. Take this thing, multiply by this number. That's a multiple of I. And then I have to do the same thing here. This is all of this thing is a number times this, which is another number, and collect all of them in one place here. That's going to be multiples of I. Do the same thing for j that shows up, and then I'll be halfway. Still have to do stuff. So this times the first one here. So what do I get? So I have a times a squared, that's an a cubed, omega squared times another omega squared, that's omega 4. Then I have c times s squared. So let's keep track of all of these things. So I have a minus, I write minus, a and a squared, so I have a cubed, omega squared, that's omega to the power of 4. Then I have a c and an s squared, so I write c, that's cosine of omega squared, and then s squared, that's sine of omega t squared. Okay, how about the other one? This times same, so that's another number here I have to multiply by the I. So I'm going to write that one minus, I have a, okay, I have a b squared, similar things next to each other, omega squared, omega squared, omega to the power of 4, c times c squared, that's going to be c cubed, excuse me, let me correct, this is times c cubed. Okay, in the second one we have a little bit of an easier time. There's just one term here multiplying by a omega, minus and minus makes a plus. So now I have a omega, and omega 3 becomes a omega 4, so it becomes a omega 4, s times s becomes s squared, and then I have factor of a squared minus b squared. Okay, and do you appreciate that I made that abbreviation of cosine of omega t and sine of omega t? Yeah, otherwise this would by itself would have run through 2 lines. Now all of this thing has to be repeated for j. So here's I have my j here. This is a coefficient, that's another coefficient. These two have to be multiplied with each other, and that's what I'm going to do first. So b a squared, so I have minus b a squared, omega squared, that's omega to the power of 4, s times s squared is s cubed times the second term. I have b times b squared is b cubed, omega squared, omega squared, omega to the power of 4. S times, I have s times, I have a s here times c squared, so s c squared. Now I come here and duplicate all of this effort that I had over here. I have minus b omega cubed c cs, so I write minus b omega to the power of 4. Then I have c times s, c times s, so the c squared times s, and then I'll have that factor of a squared minus b squared. No, I stand back and double check, make sure I am not missing anything. So much of this thing to be done, so it's a good idea to stand back and see if you can catch some mistakes and such. The way we are doing, we have to expect certain kind of order showing up all over the place. So for example, I check my power, so omega 4, omega 4, omega 4. It wouldn't make sense to have a mix and match of, for example, omega 4 somewhere and omega cube somewhere else. The units physically would not match, so that's a good thing that all of our omegas are the same. I have a cubed, a b squared, it's a total power cube. Here I notice I have a mistake, or do I? I have a times a squared minus b squared, so the unit of this thing is also cubed. ba squared is cubed, b cubed of course is cubed. I have b times this thing again, that is cubed. How about my trig functions? cs squared, okay, that's cubed. C cubed, that's cubed. S cubed, that's fine. This is total power cubed, total power cube. I notice something is a bit odd here. Is s squared by itself, and it's not matching everybody else. So I go back and check, where did this thing come from? This thing came from when I multiplied the first term, this I term here, with all of this here. So let's go double check. I have my a, omega and omega cubed is omega to the power of 4. This is s has to be multiplied by cs. S multiplied by cs would have been cs squared, so I'm missing a c here. So I'm catching my mistake that there had to be a c here. So unit analysis and checking to see that your expression has a certain symmetry to it and everything is in it is an important ingredient. So again, physically speaking, our omega has to be same power because it's a unit of time over there. All expressions have to have the same power. We have some dimensions in our problem. In our problems we have a and b. These are two dimensions like the axis of the ellipse and such. We see expressions such as a cube. What does that mean? That's like a volume. Then if one expression is volume, everybody else has to be in the units of volume. This has to be volume. A times a squared minus b squared, that's volume, 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 and another volume here. Like if I had some expression here such as just standalone b squared, that would not be correct because this is a unit of area, these others are units of volume. So that's another trick we use from physics to check our calculations in mathematics. Unit analysis, everything should match. Okay, now we go back to math. We go, okay, we have to clean up. So clean up stuff that we have done in high school. We are doing the same thing. Okay, to help us do this thing, let's factor as much as we can outside. So I see that obviously everybody has a omega 4 to themselves. Omega 4, let's take that outside. I have cs squared, c cubed, cs squared again. Well, Let's take a factor of c out, so omega squared c. Then I have a common to everybody, so let's take the a out. And well, I'm running out of everything that is similar to all of them, so let's take this piece out and then see what is left. Well, from here I have minus a squared s squared. From this one I have minus b squared c squared. From here I've taken a, c, and omega squared, so I have now just s squared times a squared minus b squared. So that's looking promising that things are going to clear out. From the second one, what can I factor? Let's take a j. Nicely enough, all of these things have omega 4. They better have same omega in them. All of them have b's in it, so I factor a b. All of them have a s in it, so I factor an s. Now I see what is left. b, I have minus a squared s squared. Took a b out, so there's a b squared in it, and there's a c squared in it. So, and then from the last expression here, we have taken s out, so it's a c squared times a squared minus b squared. One more round. I omega 4, let me write a first, c, minus a squared s squared plus a squared s squared, so they cancel out. I have minus b squared c squared and minus b squared here s squared. That's nice. From the second expression, I have j omega 4 b s. So again, I have minus b squared c squared, and this plus b squared c squared are going to cancel each other out. This is minus a squared s squared, and then minus this is a squared c squared. One more round of simplification. I have b squared is common to both of these things. I factor it out, so minus I omega 4 a b squared c times what's left, c squared plus s squared. Same thing here, minus j omega 4 b a squared comes out times s times, this is also c squared plus s squared. Now what do we remember from trigonometry? Of course, so it is cosine squared plus sine squared, 1. Cosine squared plus sine squared, that's 1. So this becomes minus I omega 4 a b squared c minus j omega 4 b a squared s. And of course we are going to clean up one more round. I'll have minus omega squared, omega to the power of 4 a b is common to both of them. Now it's going to be b c I. So from the first one I have b cosine of omega t I plus a sine of omega t times j. Okay, it took a while, but we got something clean. Omega, numerator of that expression, I have the following: minus omega to the power of 4 a b b c I a s j. I want to take a break now. But, so that's my W. Let's go back and see. We did all of this work because of what? Normal vector has this numerator and you have to divide by itself, so I separated the numerator, called it W. So W was the numerator. And then I wrote out what the ingredients were, multiplied it all out. After quite a bit of wrestling, that's what's left. Now, what was n? N, normal vector. So this is unit. So what is this? W over length of W. So that, of course, that's minus omega squared AB. Of course, my handwriting, I hope you don't get confused. So omega, and that is W. AB BCI plus ASJ. I made a mistake already. It is 4. Length of this. Okay, this is a multiple. So I'm going to have the length of this is going to be, well, of course, absolute value omega 4 AB times absolute value of that. Absolute value of that vector is going to be b squared c squared plus a squared s squared. Now we said omega is, well, whatever omega is, this and that one, they are going to cancel each other out. AB and AB are going to cancel each other out also, except that their signs, we have to be careful about the signs. So there's going to be a little bit of strange thing, AB over absolute value of AB. So this is either +1 or -1 depending on what kind of signs you have for A and B. The rest of it, very clean expression, BCI ASJ, and then divided by length of that thing, which is b squared c squared plus a squared s squared. Okay, just to keep things simple, suppose we have a situation that our A and B are positive. Most of your homework is like that. A and B are positive. So these two AB becomes positive. Its absolute value is itself. When this simplifies, just a minus survives. So let's write that example. So minus stays here. Let's write everything else in an expanded fashion. So in case, I hope you followed through, this is cosine of omega t I, a sine of omega t j divided by, okay, b squared cosine square of omega t, a squared sine square of omega t. So if you want to write it in a full expanded version, that is what it is. If an A and B, both of them were negative, it's the same thing. If A and B were of opposite signs, this, so let's write it. So if A negative or B negative, still the same thing. If A was positive, B was negative, or A was negative, B was positive, it's going to be plus same fraction, excuse me, not writing it, is exactly the same thing, just that in front we have now a plus. Okay, we made an achievement. We have come all the way to n. Now it's downhill from there, everything else straightforward. K, that's curvature. That's one formula, that's another formula. It's your choice which one you want to do. Dot product is always easier than a cross product, but be my choice if you my guess if you want to do something else. So that's going to be straightforward, and also these two are going to be straightforward. Since I have n, I can calculate a dot n easily, but let's go step by step. So since I have a dot n here and also here, let's just calculate that. So a dot n which has a name. It's a normal component of acceleration. Like when you go around the curve, you get pressed against the door of the car. That's because of the force that you need to stay on that circle track. The normal component of acceleration comes from there. That's the acceleration you have at that situation. So if we want to do that, so I have to write A itself was A. I'm going to copy A. There was our A. I'm going to copy this, or this is also A. Okay, so I'm going to take that, multiply dot with n. So I'm going to take whatever. Let's pick this one. So A from up there, A omega squared Ci minus B omega squared Sj. That's acceleration. Then times this one. Let me put all of this in one parenthesis so that it doesn't clutter too much. And then the rest of it, okay, so let me put this one in up front, and then so this minus and these minuses, maybe it becomes positive, AB over AB, and then dot the I with the I. So let's write that. So I'll have A omega squared C times C is a C squared. In A dot B, let me write the B next to this one. In the other one, this one times this, so it's going to be another AB. So remember, this minuses cancel that minus over there. S times this is S. I have another omega squared, and then S squared. Denominator, I have, here's my favorite expression here, in the denominator. Well, AB, AB, AB here, you can write it A squared B squared over AB, omega squared C squared plus S squared, that's just 1, so in short, A n or A dot n, now A squared B squared over absolute value of AB, you can just write it absolute value of AB omega squared over let me write my A first, maybe it's your choice, plus B squared C squared. So we got one more thing. You're wondering when is this thing going to end. Pretty soon. So one more thing, let's do that too. Tangential component of acceleration sometimes comes in problems. A dot t. So again, I have the A somewhere all the way up back. A. Okay, A was easy. So here's my A, and where's my T? Can somebody show me where is my T? Okay, here's my T. So I have to multiply that A with this T, and then I'll be done. Well, almost. So my A was minus A omega squared ci minus b omega squared sj. That's my a. My t was easy, minus asi plus bcj over a squared s squared plus b squared c squared. Okay, first with first, so it becomes a squared omega squared cs. Second expression becomes minus b squared omega squared, that's also cs or sc, divided by this expression that keeps showing up all over the place. So of course we factor things out, because this is omega squared cs times a squared minus b squared divided by this expression a squared s squared plus b squared c squared. You can every now and then you can check some things. For example, if you said a is equal to b, meaning you're going on a circle at a constant frequency, then well, there's no tangential component of acceleration, and so let me capture it like this. So this is a quick check that something looks reasonable here. If I was on a circle, my tangential component had to be 0, and this one indeed shows that. Okay, finale of this thing. I never thought it's going to be finishing, but this is actually, I promise, this is the last curvature. So let me write here, this is normal component of acceleration. This is tangential component of acceleration. So now we are going to calculate the curvature. You have half a dozen formulas there. Pick on one of them. So we set a dot n over v squared. In your mechanics classes, you're going to see v squared over r is your normal acceleration. This is actually the same formula. So a dot n, we had calculated it before. Let's see, a dot n, thankfully we have done this. And then v squared, see if we can avoid drowning this. Okay, this is my v squared. I just have to divide the two of them, and then so a dot n, let's see, this is a dot n the v squared, what was v squared? Okay. Here's the v squared. That one also has omega squared times a squared s squared plus b squared c squared. Omega squared cancel. I get ab. These two are the same expression, a squared s squared plus b squared c squared, power 1 power of a half, a total power 3/2. So that's the curvature. So if a, b are positive, we can just drop this. A squared s squared plus b squared c squared 2 power of 3/2. Okay, so that's a style of calculation in this section. We were just going on a recognizable trajectory of an ellipse, so the formulas have a certain flavor to themselves. We are going to come across some homework problems that are similar to this. A and B and omega are some given numbers like 2 and 7, and maybe omega is pi and something. I hope you go sit down and do it all from scratch and compare against what we did here. Okay, until next lecture, good luck and God bless.